If you get your hand and you hover it over the top of a candle, your hand warms up, but there's no air current. There's nothing touching you. So how is this heat getting to your hand? This is radiation. By the end of the video, you'll understand how heat can travel through space itself, how it's measured, and why your clothes, skin, and your cookware all interact differently with heat. So before we look at the math, let's have a visual anchor. Imagine you're in a freezing room. You stand near a fireplace. Suddenly, you feel heat. You feel the heat onto your body, but there's no wind. That is radiation. Now, what if you put your hand above the stones of the fireplace? So you get your hand like that. It also feels warm. That's because the stone absorbed radiation and now it's radiating back to you. The idea of radiation is that heat energy carried by light in the infrared range doesn't need particles. So radiation is invisible. Infrared. We can't see that with our eyes. It doesn't need a medium like sound does. That's why the sun can heat up Earth, but you still can't hear in space because waves like sound need a medium. It doesn't need contact. You don't need to touch anything. We quantify radiation like this, with this equation here, which I'll break down after writing it out. In plain English, this means power. So if you remember from work and energy, power is the energy being radiated every single second. This is emissivity, which means how good the surface is at radiating stuff. This is the Stefan-Boltzmann constant. Let me write that out because that's also the name of the equation, the Stefan-Boltzmann equation with this constant. And this constant, you don't have to remember it, but it is on the free cheat sheet in the description, is 5.67 times 10 to the power of negative 8. It's just like the gravitational constant. You don't need to know it, but it is part of the equation and also part of the final calculation if you want a numerical value. The unit is watts, meter squared, Kelvin to the power 4. A represents surface area of the object, and T is your temperature in Kelvin. So that's the entire equation. How does temperature work here? You see, this is to the power 4. So your radiation is proportional to temperature. That means with a tiny increase in temperature, it causes a huge explosive increase in radiation. What is emissivity? Black rough surfaces have an emissivity of roughly 1. That means they are excellent emitters and excellent at absorbing. Shiny silver surfaces that are very reflective, they have an emissivity of roughly 0, so they are sucky at emitting, but they are good at reflecting. Think of radiation as a glow. So a hot coal, it glows red. That glow is also infrared. The sun and Earth, if you look at it like this, the sun glows in all directions, radiating everywhere. Earth catches a tiny fraction. Even when you can't see it, radiation is leaking energy out of everything around us. And here's a more advanced variant of the equation, which we need to look at before we solve some problems today. When the object is surrounded by an environment, but the object has a different temperature to the environment, you need to find the net energy flow with this equation. It's similar to the base equation, but for temperature, it's the difference between the temperature of the object and the temperature of the environment. This gives the net flow of energy. If both are the same temperature, then there's no radiation being transferred. Let's go through an example problem. So imagine you have an athlete, and this athlete just finished a big game. His skin has a temperature of 34 degrees Celsius, and the room he's in, the locker room, is 15 degrees Celsius. How much energy is he radiating per second? First, let's assume some values. Let's say the surface area of his skin is 1.5 meters squared, and his emissivity is 0.7. Now, let's solve for how much energy is he radiating per second. Take our equation, which we just wrote out here. This represents the temperature of the athlete. This is the temperature of the walls. We have to convert it to Kelvin, first of all, and to convert Celsius to Kelvin, you just add 273. So 34 degrees Celsius for the athlete means that the athlete has a temperature of 307 Kelvin, with the walls having a temperature of 288 Kelvin. We're ready to substitute in to find how much energy he's radiating every second. His emissivity, 0.7. Boltzmann constant, I'm not going to write it out, but just know the number is there. His area, 1.5. And his Kelvin to the power 4 minus the room Kelvin to the power 4. The final answer is roughly 120 watts. So the athlete is radiating 120 watts. He's basically a heater while he's standing still. Here's another problem. It's a little bit different. You have two sealed cups of coffee. The first cup of coffee is matte black. The second cup of coffee is polished chrome. It's shiny metal. They are identical with everything. So they both have 0.5 kilos of water. They're both 95 degrees Celsius. And this exposed surface area is both 0.5 meters cubed. And they both have the exact same exposed surface area of 0.05 meters squared. The room they are in has a room temperature of 20 degrees Celsius. And you leave them out in this room for 30 minutes. The emissivity of the matte black coffee is 0.7. The emissivity for the shiny one, 0.10. It's worse at emitting because it's more reflective. The problem we're trying to solve here, compare how much each cup of coffee cools down by radiation only. How do we approach this? We have to do something a little mathematically heavy here. If you take our two equations, which I'll quickly write out, and the other one back from thermal energy, which was Q equals MC change in temperature. And these are both on the cheat sheet, but if you combine them, substitute this in for Q, and then go through a lengthy rearranging process with your excellent math skills, then you get this resulting formula. Change in temperature equals all of this stuff divided by MC. And why did we do that? Well, because the main formula for radiation of this video, it wasn't enough. We're looking for how much the cups cool down. And we can't do that with just this formula. We needed this variable here. So we took a formula like this, which has a lot of connections. We could substitute it in. And it includes the variable that we're looking for. You won't always need to do fancy stuff like this, but I want to introduce to you a few more difficult problems. So we know everything here. We can substitute in everything. Take a look. And by the way, this is change in temperature for one thing. So we would substitute in the temperature, the emissivity, the area, the mass for these one at a time. And if you do that, you find that the matte black kettle has a change in temperature of 18 degrees Celsius. So it goes down in temperature by 18 degrees. The change in temperature for the shiny chrome coffee cup is only 2 degrees Celsius. You'll find that with math. Higher emissivity was the only difference between the two cups. Every other property was identical. It shows that having a higher emissivity means faster heat loss. And the shiny one reflects the infrared and traps energy, while the matte black one emits infrared and cools very quickly. So even though both of these coffee cups had the same temperature and shape, the black one dumped all of its heat 9 times faster just because of surface finish. And that's the power of emissivity. And to finish this video, here's a little fun fact. If you lie down in the sun on the beach, it's a nice warm day, your body actually absorbs 0.5 kilowatt of warm heat. That's enough to run a microwave.